So we're going to look at electron flow and conventional current. And just reading from the handout we have here, when electricity was first being investigated, the electron had not yet been discovered. At the time, it was believed that electric current flowed from the positive terminal to the negative terminal of a battery. Now, just to go back through some history, now they knew how to create electricity from chemical reactions and how to make a battery and not. So they knew what electricity was, as in they knew it can shock you, they knew it can heat up something, they knew that it could create light. But to say they knew what it was made of, they knew nothing at all as yet. All right, it's kind of like thinking about if you all were eating cake. Would you all know that cake had egg in it? Anybody? Nobody. All right. Now let's think about it. Eating cake, you would not know that cake had egg in it. You'll know it had sugar. You would know it had some spices, right? But you wouldn't know exactly what it was made up of until you were able to break it down. Same thing here for electricity. They knew what it did, but they didn't know what it was made up of as yet. But that didn't stop them from devising rules and learning to see how it behaved in circuits and whatnot. So they came up with rules, they came up with explanations that they had at the time. So at that time, reading from the handout, it was believed that electric current flowed from the positive terminal of a battery to the negative terminal of the battery. Now, this made a little bit of sense at the time, because if I have a circuit, all right, if I have a circuit, right, I have my positive terminal, my negative terminal, it's going around, you could put, some device to record it. They thought they knew everything had equal amount of positive and negative charges so that, it will be even. And they thought that the positive pole in a battery gave off electrons. They emitted electrons. That's how the positive pole became positive. Let's look at it here. If we have some degree or amount of charge, and I took away some negative charges, what will be the majority here? Positive or negative?
Positive.
Positive. So this is, it was okay logic at the time. It made sense. If the positive pole was giving off electrons, then that means that my pole will remain positive, right? The more electrons you give away, the more positive the pole became. Now that made sense at the time. But then we come up to the law of electrostatic attraction that blew this out of the water completely to say that, this is not what's happening. Electrostatic attraction, where we have like charges repel and unlike charges attract. All right, we had done that at the very beginning of the handout of electricity. Now, these electrons will now move through my circuit. Question? No problem. All right, somebody else asked a question or said something. All right, so we have electrons moving through my circuit. Now, will my negative electron be attracted to my negative pole, or will it be repelled by my negative pole? I have negative and positive poles. Will my, answer?
It will repel because of the electrons and the negatives will be I will repel.
Very good, right? So this is the point here that that should have told them something. They did not know that electrons were negatively charged. They had no idea. They thought electricity was this thing that flowed from negative to positive, no, from positive to negative, but there is no way a negative pole of a battery will accept more electrons, strictly from the fact that, according to the law of electrostatic attraction, like charges repel. So that could not work. All right, but they didn't know this at the time. They just came up with the rules because that's what it looked like. All right, this part they did not know as yet. They knew this one here, all right? They thought about this side, And that made a lot of logical sense. You know, if you took away negative charges from your positive pole is going to remain positive. But they did not factor in electrostatic attraction as yet because it did not know about electrons. So continue reading from the handout. As a result, the laws governing circuit algebra follows the direction of positive to negative. So this is the direction we're going to use when we're doing all our calculations, all our circuit drawings, all our analysis. Take from positive to negative. These are the rules are written using this direction. Years later, reading from the handout, years later, when the true nature of electricity was understood, it was shown that electricity actually flowed from negative to positive. Rather than rewrite all the laws and rules, it just rename the directions. So what we have here, the direction, the old direction of positive to negative is what we call conventional current, right? This was the old convention. But the movement of electrons, which was the actual movement of electricity, moves from negative to positive. And we call this electron flow. Please note we use current in the conventional form. We use conventional current in all our calculations. So to show, note here, all the rules in electricity and magnetism follow conventional current, which is positive to negative. I'm going to always remind you all of that until we remember it. So don't stress too much, you know, which one is which. Always look at conventional current is from positive to negative. So we have two ways of representing this. When we have a battery, remember the long pole is your positive, the short pole is your negative. When we want to indicate conventional current, it is written as an arrow on our wires itself. That is conventional current. Anytime you will see a circuit, you're going to see an arrow on your connecting wire, and this indicates your conventional current. Now, if I want to indicate where my electron flow is drawn as an arrow outside of your circuit. So this is how we indicate electron flow. All right, so just note the difference. The only direction that we are going to be concerned with in all our calculations is conventional current, and that's from positive to negative. So moving on, we have Kirchhoff laws. Oops, hold on. Right here. Right, Kirchhoff laws. Circuit algebra follow Kirchhoff laws. Kirchhoff is a Russian physicist who had worked with George Ohm, right, way back in the 1800s. So they came up with a lot of the rules in how to work out the direction that current flows in, how much voltage changes, and whatnot. So there are rules, there are ways to work out our values. They don't just exist haphazardly, they change predictably. So that's how we could end up with formulas, or we could end up with math rules to tell us how our current and voltage changes. So the first law, all right, let's look at our first law. We have, we're just going to look at the first law at your level. All right, so this law helps in determining the magnitude of current flowing in parallel circuits and branches. So before we start that, let's identify what's a series circuit and what is a parallel circuit, because I don't know if you all would have done this before anywhere. All right, so a series circuit is one where we have a power supply and everything is collected across a same line. All right, something like this is what we call a series circuit. Everything is connected across one line and directly towards the power supply. When we have a parallel circuit, right, we have the existence of, branches, or some people like to call it ladders. Students have come up with that term. So I will have my power supply. Remember, the long is the positive and the short is the negative. So I have my components looking like this in ladders. All right, so they don't form one line to the battery, they actually break off and go into different sections. Or I can look like this, where I have a branch for my current to go into different directions. So when we have series and parallel circuits, the way how the current breaks up and the way how the voltage changes is different in both sections. So we have to learn how to deal with both series circuits and how to deal with parallel circuits. Now, each circuit has their own advantage. They all do series and parallel circuits in form 3. No? All right. You were supposed to have touched on it a little bit. All right. But we'll get there, don't worry. Right. So we have series and parallel circuits. So Kirchhoff's first law, this law helps in determining the magnitude of current flowing in parallel circuits and branches. So we're going to look at how parallel circuits operate. All right, then we're going to see about series circuits. So we read in here in the italics, at a junction in a circuit. Now a junction is where your current breaks up and goes into different directions. Just like in a junction in a road, you know, you reach a point where you break off and go into different directions. Same thing, right? So at a junction in a circuit, the current entering equals the current leaving the junction. Suppose I have here current I. This could be any value. You could have 1 amp, 2 amps, 100 amps, whatever, right? Suppose I have current I. It reaches a junction and it now splits off into 3 different parts. I have I1, I2, and I3. What they said, at a junction, the current entering, which is I, is equal to the current leaving the junction, which will be the total of these 3. So it will be I1 plus I2 plus I3. That's simple enough to understand. You all know if you have a group of people walking on a pathway, they can choose to go off into different amounts along each pathway. And you're still going to get the same amount of people when you add it up at the end of the day. All right, so we have to be able to identify our 2 branches and how our 2 branches work. So this is our first branch here where it forms, you know, kind of like in a triangle angle kind of way. Or we have the normal regular one that we see in class and we see in exams, which will be the square branches. And what happens here, it's the same thing. We have the current going into our junction. It reaches that junction and now it splits up into 3 different pathways. So you're going to have I1, I2, and I3 here. Now, if we were to draw this back here and they go back into a wire, what's going to happen? These 3 currents are going to come back and join up to form back I. Is everybody okay with that? That's really simple to follow, I hope. Anybody? You all good so far?
Yeah, miss.
Good. All right. Now, in a parallel circuit, the current is different in each section. You have to remember that. So you can put that down. One, in a parallel circuit, all right, your current breaks up. And here we can see what we have. The voltage across a parallel branch is equal. Now, voltage tells us how much energy is in a section. So the way how this works nicely, all right, once we have a parallel section, all right, once we have any sort of parallel section, parallel circuit section, our voltage breaks up or not breaks up, it shares itself evenly across each branch. So let's learn, these are both parallel circuits, all right, or parallel branches, same thing. All right, so you just have to remember in a parallel circuit, your current breaks up and your voltage remains the same. So those are the two rules we have to remember right now. All right, you just have to remember them. We're going to refer back to them all the time, don't worry. So for circuit resistors, we have to be able to add up our resistors in our circuit because we can always, when we have a circuit, let's say that's our circuit, it has a resistor, R1, it has an ammeter, right, and so forth. We will know what is the voltage coming from the battery because it will be written on the battery. Sometimes we will know what is the current being delivered by that battery. It's usually written on your battery. If you all today get some time and look at any battery you all have in the house, you're going to see somewhere written on it, it has 1.5 volts written on it. Anybody ever notice that?
Yes, miss.
All right. So your batteries actually do have the voltage written on it. So you have your voltage on it, you can read your current, and sometimes we have to determine what our current is, we have to determine what our resistance is, and sometimes we have to determine how our voltage changes. And the first thing we have to do here is to know how to add up our resistors. Now, adding up our resistors is not very straightforward. Sometimes it is, and other times it's not. So according to the syllabus, you all have to be able to derive the formula for series and parallel circuits. Derive the formula meaning to show how that formula was, well, not derive, but how we came up with that formula to work out your series resistors and your parallel resistors. So let's go into series resistors. So I have a series circuit here where I have R1, R2, and R3. I have my positive side of the battery, so my conventional current is coming out of the positive side of my battery, all right, and it's going to be going around my circuit. My battery is producing a current I. Now, the way this works in a series circuit, remember your current tells us how many electrons are flowing in your circuit. So if I have, let's say 1,000 electrons flowing in my circuit here, 1,000 electrons are going to flow through my first resistor, 1,000 electrons are going to flow through my second resistor, and the 1,000 electrons are going to keep on flowing. So this, why I'm saying this, this is going to lead us to say in a series circuit, your current remains the same. And I have it here written, your voltage is going to vary. Whoa, that was horrible handwriting. All right, so your voltage in each resistor is going to vary depending on the resistor value. So always remember that the current remains the same and the voltage changes. So look at our rules here. The current through each component is the same and the voltage varies. Looking at the diagram, all right, we can see that we have V1 across our first resistor, we have V2 across our second resistor, and we have V3 across our third resistor. Remember, voltage is a measure of energy, and your battery is not going to create extra energy, nor is it going to give up a lot of energy. So we make the assumption that the voltage created by our battery is equal to all the voltages in our circuit. So V is equal to V1 plus V2 plus V3. You can say sum of voltages is equal to your battery voltage. All right, so here the individual voltages in each dry cell, or no, in each resistor, right? So we have each resistor here has its own voltage flowing across it, and the sum of these voltages will give us the total voltage. So we're going to use this now. We want to determine our current and our resistors in our circuit. So we have V is equal to V1 plus V2 plus V3. What is the most popular equation in current in electricity, all? We did last day. We did with the triangle. Anybody
V is
who's
equal
right?
to IR.
V is equal to IR. This is the equation. This is the big equation we have in our topic. All our equations can lead back to this very simple equation. So V is equal to IR. Remember this. Remember your triangle. All right. Remember your triangle here where we have V and we have I by R. So we're going down. So using V is equal to IR, we replace the V's with I and R's in order to find the total resistance. Remember, we want to find the total resistance in series and we want to find the total resistance in parallel. So what we have here, let me see if I can get the diagram back up. Right. So my total V will be my current by my total resistance. So that's going to be I by RT is equal to, what is my V1 in my first resistor going to be? It's going to be I by R1. So we get I by R1. My V2 is going to be I by R2. So I'm going to get I by R2. And my V3 is going to be I by R3. Everybody follow that? For each V, all right, we get I by R. So we can actually, the way I wrote it down here, you can just multiply one term by the next. All right, one term by next. Remember, each resistor has the same current. They have different voltages. Are you okay? Yeah,
Yeah.
good. All right, it's relatively simple enough. Now let's just go here into the maths. All right, zoom in a little bit. We have I by RT is equal to IR1 plus IR2 plus IR3. Now we can factorize out the i's. You all know how to factorize out a common term. So we pull it out of the brackets and we're going to get I by RT is equal to I open brackets into R1 plus R2 plus R3 close brackets. Now I realize here that I is common on both sides of my equal sign. So I could go ahead and divide by I and cancel out the i's. All right, this is simple algebra. You also know how to cancel your like terms on both sides of the equation, the equal sign. So by canceling the i's, you're going to get the total R will just be the sum of my resistors in a series circuit. All right, so in series circuits, to add up your resistors, all we're going to have to do is just find the sum of our resistors and we get our total resistance. Let's go on to parallel circuits. Now, parallel circuits is a little bit more, right? But not much more. All right, so to get for parallel resistors, we have to remember rules. First things first, the rules are opposite to the series circuit. What are the series circuit rules? One, our current is the same and our voltages vary. So what's the very opposite of that, y'all?
Must the current vary and the voltage the same?
Yep, the current varies and your voltage remains the same, not small, same. All right, so here we have, and we just did Kirchhoff's first law. Kirchhoff's first law told us when current reaches a junction, it is going to break up and to go into different parts. And if we look here, we have a junction. So our current is going to reach our junction. It's going to break up into I1, I2, and I3. So we can see that our current varies. And the way how this works, our voltage in each branch is going to remain the same. So if our voltages remain the same, we're going to look at what are we adding up in this circuit. We're going to be adding up our currents. So note here, the voltage across each branch. Now I said each branch is the same. We're not just looking at the individual pieces inside of these circuits. All right, suppose I had a next resistor here. All right, what we just looked at, the voltage across the entire branch is equal to the next voltage of the other branch. So be very careful. It's not a component value we're looking at. We're looking at the entire section, or each branch or each ladder has the same voltage. So the rules here, the voltage across each branch is the same. Sorry. And the current breaks up at the junction. So let's zoom out a wee bit. So since the voltage is the same, we will look at the current relationship. And the current relationship here, according to Kirchhoff's first law, where I is equal to I1 plus I2 plus I3. That's Kirchhoff's first law. So what we're going to do, from V is equal to IR, we can find that I is equal to V over R. Let's check our triangle and see if that makes sense. V is equal to I by R, and I want to find out I. All you have to do is just cover the I to find what you want, cover the I, and you're going to be left with V over R. So what we're going to do, instead of writing I's, we are going to be writing V over R. So let's try it for our circuit diagram at the top here. My circuit here is producing a current of I. It has a main voltage of V, and my total resistance will be R subscript T. So if we have I is equal to V over R, my main current is going to be the main voltage over your total resistance. And now let's do the individual I's. If you do the individual I's, all right, we're going to have I1 is equal to V over R1 plus, if you look at I2, you're going to get V over R2. And then if you look at I3, you're going to get V over R3. Everybody follow that? Or you want me to go through it again? At Form 4 level, I assume silence means no. Let's go through it again.
Yeah, miss, you can go through it again, please.
That is what I'm going to do. All right, so we're going through with a fresh pen. All right, so I have my battery has a voltage of V. It is producing a current of I, and the total resistance will be R subscript T, R total. Now here we do know, since the voltage across each branch is the same, we cannot add those up because it's the same thing. But we're going to use Kirchhoff's first law. And Kirchhoff's first law states when a current enters a junction, it's equal to the current leaving the junction. So I is equal to I1 plus I2 plus I3. And we just looked at here to see that I is equal to V over R. So let us get V over R relationships for every I. So I have here my I1. Let's see if we can get a little bit bigger. Right. So my I1 is going to be V over R1. So I'm going to get I1 is V over R1. Remember, the voltages in each branch is the same. So that's how I end up with V. My I2 is going to be, if you look here in the diagram, I2 is equal to V over R2. So you're going to get V over R2. And if you want the I3 is here. It's going to be V over R3. We get it now? Yeah. So now that I have all my terms with V's and R's, I can start to do some cancellations, because if you look here, let's just zoom in a little bit. Let me write it over. So you're going to get V over RT is equal to V over R1 plus V over R2 plus V over R3. Since the voltage is the same, we can cancel it out. Even though it looks like you have multiple V's, we can go ahead and factorize this out, sorry, to save. I lost my pen, hold on. Oh, there we are. All right, so we're going to have V over RT is equal to V over R1 plus V over R2 plus V over R3. Since V is common in all, we can factorize it out to give us something like this. We're going to get V into 1 over R1 plus 1 over R2 plus 1 over R3. If you're not too sure on how we're going to expand that, remember when we expand in brackets, we're just going to multiply what's outside the brackets by each term. All right, so that's how we were able to pull it out of the brackets. So we end up with V over RT is equal to V into all of these. Now, if I divide by the V's are now going to cancel each other across the entire circuit. So what we're going to do, we're going to cancel one V and it's going to cancel the other V. And we're left with, remember, V divided by V is how much? Anybody? V divided by V is what?
1.
1, good. It's not 0. Lots of people make the mistake of dividing same terms and getting 0. Don't fall into that. So we're going to end up here, and we end up with 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So note we are adding fractions here. The addition of fractions is much different than the addition of numbers. But we are not finished yet, because I have 1 over RT. I didn't want to find 1 over R total. I want to find R total. So what we do to get, hold on, right? To get our total resistance, we invert our answer. Inverting our answer, we're going to be using our calculator X minus 1 button. You all get your calculators. Tell me if you can go and find the X minus 1 button right now. I think we did this last day or some time ago, but that's verifying with you all. It's usually second function X squared, or a button by itself. Everybody sees, tell me if you find the X minus 1 button.
Yes, ma'am.
Good. Anybody else not finding it? Still looking? Okay. Right, when we do any questions, you'll find it. Well, you'll have to know it anyway. So in order to get R total, all I did the inversion, inverted it. Inverted it means just to use the X minus 1 or to turn it upside down. Please note that when you're adding fractions, you cannot go and say, well, if I have 1 over R plus 1 over R, and I do the X minus 1, that is not going to be equal to R1 plus R2. It's very different. And how is that different? Let's put in some numbers and check and see how this here is a horrible mistake to make and to assume. Do not do this. All right, let's just put in some numbers and check. All right, everybody, if I have R1 is equal to 4, R2 is equal to 5, right? If I have R1 plus R2, what will I get? Anybody?
9.
9, good, right? Now let's do it in fractions. If I have 1 over R1 plus 1 over R2, somebody tell me, will I get 2 over 9?
No, miss.
No.
Same.
Right? There's no way you add fraction like this. This is madness. A primary school child will look at me and say, Miss, no, that's wrong. Remember, when you add in fractions, we have to go put in our numbers. We have to find our LCM. Our denominator goes into our other denominator, and then we multiply by the numerator. And we end up with 9 over 20. See the very big difference in adding your numbers with fractions and with whole numbers. So please do not make this mistake here. You all see this mistake here. You cannot assume, well, yeah, if I invert 2 fractions and add them, I could just add them. It does not work that way, because the addition of fractions is inherently very different to the addition of regular numbers. So please, you all, do not make this mistake. Don't do it. Don't do it. All right, I could scream this whole day and tell you this whole day, and somebody exam will still come and do this piece of specialness. Trust me. So let's go ahead and let's try some questions. All right, some of these you can do mentally. Honestly, some of them you can do mentally, and others you're going to have to put in a little bit of brain work to try. So this is where we're going to get an assignment this afternoon. We're going to get quite a few of these to try, and we're going to do pretty okay with them. Pretty fun after the end of the day. Right, so I want to add, I have R1 is 10 and I have R2 is 5. Let's find R1 and R2 added up in series and in parallel. So in series, I know the answers are there, but we all can still work it out. R total will be the sum of my resistors, which will be R1 plus R2. So what is my total resistance here? If R1 is 10 and R2 is 5. It's written there.
15 ohms.
Right, we will get 15 ohms as said here. Now, if I want to do parallel, this is how you all are going to do it in the calculator. You're going to get R total is 1 over R1 plus 1 over R2 to the minus 1. So let's use our calculators, because remember, we're allowed to use calculators for all our physics questions and exams. So it's your good friend. Let's go ahead and try. So what you're going to do, everybody get your calculator out. We're not going to use the fraction formula. We're going to use the x minus 1 button. So this is what we're going to do. Let me just make sure I have the right. So first things first, we're going to hit 10 x minus 1 button. Is that it? Yeah. First step, 10 x minus 1, 5x minus 1, and you hit equal. Tell me what you'll get when you do that.
0.3.
You get 0.3, right? This is not the answer, because we still have to go and find the inverse of this. So the second step you're going to do, you're going to just take that same answer. All right, so you're going to take the same answer and hit the x minus 1 and get your final answer. And you always put your numbers to 2 decimal places. So you get 3.33 ohms. You all got that?
Yes, miss.
Now we could do this the long way, the maths way, because again, I like maths and I always do stuff in maths. Let's just try this the regular maths way and see if we'll get it. 1 over 10 plus 1 over 5. What is the LCM of 5 and 10?
10.
10. 10 into 10 is 1. 1 by 1 is 1. 5 into 10 is 2. 2 by 1 is 2. So you're going to end up with 3 over 10, which is 0.3. But you have to now go and find the inverse of this, which is just turn it upside down. And you're going to get 10 over 3. And 10 divided by 3 is 3.33 recurrent. So you see, you get both the same way, but get, use the calculator, know how to work with your fractions, and you can work it out. If you all want to try both ways, so you're really good in doing both ways, by all means, go ahead. All right, so let me give you all a couple more to try. All right, I'm going to write it down right here. I want you to find RT in series first, and then in parallel. So we have A, we have 5 ohms, 10 ohms, 20 ohms. So remember the 3, you're just adding the same amount. B, now this is a series circuit, so you could just go and add it as is.